The next application example is for a point moment. So again, you have a simply supported beam, and exactly at the center at L/2 you have an applied point moment of m0 over here. Now because of this m0, you can tell that there will be two reactions over here. So let's just go ahead and mark the reactions at A and B. So at A, so since my direction of the moment is is clockwise over here, the reactions must develop in a way that over a distance over L, that you will have an anti-clockwise moment. So the anti-clockwise moment meaning that at this particular point at A you will have a vertically downward reaction, and here you have a vertically upward reaction. So from B to A you are going anti-clockwise, that balances your clockwise moment, and the values of the reaction will be what? Your RA will be m0. You can easily get this by solving the equilibrium equations, but this is just by intuition, and RB will be m0 by L. I have marked the directions properly, right? So the sign doesn't matter. So RA goes vertically down, RB goes vertically up over here. Okay, now let's come over and draw the shear force diagram and the bending moment diagram. Now before we go there, remember that for a point moment, the relationships that we had looked at was that, so if you have an element where in that element, if I have a point moment m0, and say the shear force and the bending moments, we have V, M, V plus V1 and M plus M1. So this was from the relationship 4. So let's just write that as well. If you are confused that we had covered these things in our previous lecture, this relationship 4, what did that tell you? That told you that when you have the point moment, and you can simply derive from the equilibrium as well, that your m1 was equals to minus m0. Now here the sign is important because here you see the applied moment was in the anti-clockwise direction over here, and because of the anti-clockwise moment, the jump in the moment, so this is the jump, right? So the jump in the moment was a negative m0. So this is just important. You just have to keep in mind that that jump which I wrote, that minus m0, was for which direction of the moment, because eventually you have to come back and deal with the beam where the moment is applied in a particular way, clockwise or anti-clockwise. And also we had seen that your v1 equals to 0, right? So no change in shear, but the jump in the moment. So let's go ahead and write the write the or draw the shear force diagram first. So we have the SFD over here. So let's just mark the guidelines again to help us draw. And one at A, one at L. So so this is my A, B, and intermediate I have C. So for the shear force diagram, I start again from the left to the right. At the left, I don't have any option but to go with a downward m0 by L, right? So here I have downward m0 by L, which is negative, right? But I'm not marking the negative since I'm drawing in the bottom half. Now interestingly, from A to B over here, there is no other point load. There is only an intermediate moment at L/2, but I have seen from my relationship that the shear doesn't change. So what is going to happen, this line is actually going to stay a constant throughout. So it's very interesting, this problem. So this line essentially stays a constant, which you can also probably tell from the right hand side. Here your reaction is m0 by L, so once it goes to the right, it goes up, right? So here you have the entire your shear force diagram is negative with an ordinate of m0 by L. Okay, now for the bending moment diagram, maybe I should draw the beam a little below so that it does not obstruct with what I have above. So let me draw the beam here. Now for the bending moment diagram, I have the same points. This is my A, and here I have C, I have B. Now, how is the bending moment diagram going to change? Let's see. So first of all, intuition always overrides. So we have the A to B. At A, it's a pin and no externally applied point moment. B, it's a roller, no externally applied point moment. So we'll have a zero moment here and a zero moment here. Now let's follow the relationship between the, because the moment, we are going to the moment from the shear diagram. So for the shear diagram is here already. So for the moment, I know my relationship is dm dx equals to your v, right? And here I have a point of discontinuity in the moment at the point C. So let's just see before that, or in this case it doesn't matter, before or after, your shear force diagram is a constant, it is a straight line, so it is a zero. So that tells me my moment must be a degree 1, right? So that means it must be linear. So you have a linear line. So the linear line, I'm going to start with A, and what is going to be the, is it going to be, you know, below or above? It is going to be below, because here you see the slope of the dm dx at x equals to 0, that is at A, equals to the value of the shear, and the value of the shear is this negative minus m naught by L. So it is going to be, you know, a downward line. So, and that since it's a 0 degrees, it's going to be a linear line. So let me draw the moment over here. It goes from here to here. Now just to the left of this point C, what is the value of this moment? So let's just try to find that MC minus MA must be the area of the shear force diagram between C and A, that is negative of m naught by L times, you know, this particular distance, that is L over 2. So that is minus of m naught over 2. So here the value is minus of m naught over 2. Now what happens at the point C? At the point C, I have a concentrated moment, which is, you know, a local moment, clockwise m naught. And what did we see from this relationship over here? That whatever was the moment, it changed with m plus m1, where m1 came out to be minus, you know, this applied moment over here, minus m naught, but this was in the counterclockwise direction. So let's just follow the similar rule. So just to the right of C, so maybe let's just explicitly write it. So just to the right of C, what do we get? Our m plus m1. I'm just using this terminology over here, that m plus m1 will be, what is m? M was just to the left of the moment, so that is minus m over 2 over here in this particular. So minus m naught over 2 plus m1, when this moment was, you know, being applied like this anti-clockwise, m1 came out to be minus m naught. Here the moment is applied clockwise, so m1 will be plus m naught, plus m naught. So that is nothing but m naught over 2. So you see there you are having a positive jump. So from here this guy actually goes up, right? Goes up to the point of a value of a positive m naught over 2. Now after that, you know, it is going to be 0 over here, and it is going to be a linear variation because the shear force constant. So this diagram has a negative part over here and a positive over here. And here your convention, I do not mark this thing because I'm already drawing in the lower half plane, so I will. Yes, so I hope this problem was clear, where we used a concentrated moment to draw the bending moment diagram. This is the top one was my shear force diagram. This is my bending moment, empty.